Welcome back, Proviso East math students. And today we're going to be looking at angle relationships 2 notes, talking about adjacent and vertical angles. We will start at part 1 with adjacent angles, which is any two angles that have a common vertex and common side. They have no overlap. They are better known as angles that are connected. So what that looks like is if you have any kind of angle that's kind of split into two different angles, like angle 1 and angle 2, we would consider that to be adjacent. So the way that the defining features of this come into play is that these two angles, angle 1 and angle 2, have a common vertex or point at which the angle happens. And then they have this one common side right here in the middle that they both share. So one angle rotates from that point and from that point in both directions. So at this point, take a moment, give questions 1 and 2 for the practice a shot, see what it looks like for you. All right, so here's what you should come up with. Now there are multiple solutions to this. I'm just going to go with a couple just to illustrate it. But what we have here is the 3 angles that are formed by the one giant angle, so to speak. And actually there's more than that. So of those angles that are going to be considered adjacent, you've got angle A, E, B, which would be this angle right here. That one is adjacent to this angle next to it. They share this common side with this common vertex, and that second angle would be known as angle BEC. In both cases, you could rename the forwards and backwards. So AEB could be listed as BEA, BEC could be listed as CEB, with E as the vertex being in the middle no matter what. Looking at the second one, you again have several options on this one. One pair is potentially this angle, which would be angle PFQ, or QFP if you prefer. And there's actually 2 angles that are adjacent to that. The one to the right of it, if you will, is angle QFR. So the whole purpose of introducing the adjacent angles, other than the terminology side of things, it helps us really define something called vertical angles, which are a lot more useful in terms of application. So let's start off with defining these. The first thing we'll say is that vertical angles are 2 angles formed by intersecting lines. They are not adjacent. So the reason why we introduced the idea of adjacent is to really just talk about what vertical angles are not. In that case, that's adjacent. Vertical angles always have equal measures. This is also known as congruent. So the big difference between equal and congruent is that equal is referring to like numbers and values. 10 degrees equals 10 degrees, etc., etc. Congruent is referring to more like the shape, like 2 objects are the same size and same shape. So congruent is a little more of the geometric side of things, whereas equal is a little bit more of the algebra side of things. So what vertical angles really look like is if you have 2 lines that intersect and they form a total of 4 individual angles. There's actually more if you break it all down, but we're going to look at these 4 angles. Angle 1, angle 2, angle 3, and angle 4. When I'm deciding which angles are vertical, I'm going to look at, for example, angle 1, and if I look at angle 2, that's adjacent to it. And if you backtrack at the notes, you notice it says it can't be adjacent. So 1 and 2 can't be vertical. If I look at 1 and 4, 4 is also adjacent. So 1 and 4 can't be vertical. The only angle that is not adjacent to 1 is angle 3. Those 2 are what we consider vertical. So angle 1 is vertical to angle 3. Now, why this is significant is because what we find out is that the measure of angle 1 being vertical to the measure of angle 3 means that they're the same measure. So what I can say is that the measure of angle 1 is equal to the measure of angle 3. Whenever you see an m in front of the angle symbol, that's referring to the measure or the value itself. So I'm saying whatever the angle measure of 1 is, if it's 60, then the measure of angle 3 is also 60. We can also look at the congruence aspect of it. So the actual shape of angle 1 is congruent to the actual shape of angle 3. So when you see this equal sign with a squiggle above it, that is where the congruence comes in. In our current set of stuff, there's really no effective difference between the two ideas. They both lead to the same concept, that the angle measure is the same. Really, the concept of congruence comes in more into play later. Okay, so now take a moment, pause the video, give this a shot. One thing to keep in mind is that you have to have two angles in order to be vertical. No such thing as one vertical angle. These are a relationship. Okay, assuming that you gave this a shot, let's take a look at some of this. Now there's actually two possible answers to number 1, two sets of two vertical angles. The biggest misconception, the biggest mistake people make is they do something like angle PUQ being vertical to angle TUS. The reason why that is not a correct answer is because this angle PQQ is formed by an angle that does not have a line side, or a side that actually creates a full line with the other angle. So that lack of a side that is splitting the whole thing stops it. On the other hand, if you look at angle PUR as a total angle, one of the sides there draws through to this side, and this side also draws through to this side, creating two intersecting lines, and the opposite side that is, or angle that is not adjacent to it, is TUS. So we've got angle PUR and angle TUS. Those two are vertical. You could have also gone with angle PUT and angle RUS. On the second problem, you've got the exact same setup, only it doesn't have quite as much complexity to it. So you've got these two angles are vertical, which is angle ABD and angle CBE. Could have also gone with angle ABC and angle DBE. Did you get them right? So now for more of the actual application of the vertical angles on a numeric point of view. So we talked about vertical angles being congruent or equal. So if I look at this very first one, I've got angle 1 and angle with the 63 degrees are vertical. And because they're vertical, that means they're equal. So the measure of angle 1 has to equal the measure of its vertical angle, which is 63 degrees. So literally, that's it. That's all there is to it. Similarly, for number 2, the measure of x is going to be congruent or equal to the measure of 119. So I've got 119. So here's a chance for you again to pause the video, give it a shot. Now these are more complicated than the ones that we just saw. I get that. Just give it a shot and then see what happens. Okay, so let's take a look at what you got here. Again, we have vertical angles going on, occurring where the measure of 2r plus 3 is vertical to what the measure of 89 is. What that means is that this angle is also 89 degrees, and that this angle is also 2r plus 3. Effectively, what that means is those two angles are equivalent. So I can take 2r plus 3 and set it equal to 89. At this point, it becomes an algebraic problem where we solve. We solve by eliminating everything that isn't the variable that we're solving for to get it alone. So I'm going to subtract 3 from both sides and get 2r equals 86, and then divide by 2 on both sides, which will yield us that r equals 43. With number 5, exact same idea. We've got 3x on one side, we've got 2x plus 16 on the other. So from there, that's not supposed to be an equal sign. From there we take 3x is equal to 2x plus 16. When you have the situation where the variables are actually on both sides of the equal sign, All you have to do is pick one and eliminate it. So in this case, I'm going to eliminate the 2x because it's smaller by subtracting 2x. So if I subtract 2x here, I balance the other side by subtracting 2x. And the good news about this is that once I do that, 3x minus 2x is 1x equals the x's here completely cancel out, leaving me with just 16. So already right there I have the answer.